Oh, sorry, start recording. Sorry, anyways. But there is also the inertia. I can say, what's the steady state? What's the transient? Maybe you remember from control course. Steady state, for example, in your starting of your motor at startup times, we call it transient. In transient, your motor draws unstable. Your sinusoidal voltage, your DC input current will be very high. What's the steady state? Steady state. Your motor speed, for example, settle down constantly. For example, your speed reference 500 RPM. Okay, your speed reference 500 RPM. Motor start up with the from zero speed, 0 RPM. Firstly, it will be in 1 second in 0.5 seconds from 0 to 600, and then it will be settled down to 500 RPM. After settle down to 500 RPM, we call it steady state. At the steady state interval, actually, your motor is stable, will be stable, your current will be constant, voltage will be constant, etc. Power, torque is constant. For example, another thing, load rejection and load injection. What's the load rejection? What's the load injection? Probably you can imagine it. Load rejection. For example, your motor works on fully load. You have a load controller. You have a button. You click the button. Please apply full torque. This is the full torque mode, full load mode. And then you can click again. Instantaneously, you will set zero load torque from full load to zero instantaneously. This is the load rejection. And load injection, if you have a no load, you will apply full load instantaneously. This is called as a load injection. Okay, it's critical. And then, but maybe we can say something about the inertia in the steady state. There is also the inertia which at any steady state doesn't really come into it, but during acceleration, for example, in electric vehicle, it's important during acceleration. So just like the inductance, actually we can say there are similar. This we will call it analogy. Electrical parameters are similar to mechanical parameters. You can see in your armature 1 over Ls plus R. You can see in load 1 over Gs plus B. What's your electrical time constant? L over I. In mechanical torque constant, G over B. There are same nearly. This is called as analogy. Sometimes you want to design a spring. Sometimes you want to design a damper. Sometimes you want to design a mechanical suspension system. Actually, if you have good electrical knowledge, you will design very easily because they are same. For example, during acceleration, the inertia, just like inductance, the inertia of the motor and the load and everything else that is a part of the connected the shaft, this will then take our torque and divide by the friction plus impedance of the inertia. Ls nearly equal Gm. This is critical knowledge for us. Ra draw as a Bm. This is critical knowledge for us. And this turns into our rotational speed. So theta is also another one. Rotational speed, I say. Theta. So theta is our rotational position. For example, in our motors, we have encoder, we have resolver, we have synchronous encoder, we have optical encoder, we have Hall sensor. Okay, generally in military and electrical vehicle application, we are using for resolver. What's resolver? Resolver give us high resolution position. Okay, we generally in electric vehicle in our design in military grade motor and controller design we are using resolver. Another high resolution position sensor optic absolute encoder. Actually, resolver is very high price. For example, $5,000. Absolute encoder, $1,000. For example, absolute encoder give us absolute position of the motor, but its resolution is smaller than the resolver. Third option, incremental encoder. Generally, in our scientific application, consumer electronic application, also electric motor bike, also simple electric vehicle, etc. We are using incremental encoder. For example, in incremental encoder, your motor rotate in 1 RPM as a mechanically. Also, don't forget it, mechanical RPM and electrical RPM are different things. Okay, you know, you remember from your electromechanical energy course, we have a pole numbers. Pole numbers give us electrical rotational speed. Mechanical speed is equal 1 RPM of the your shaft rotating. Another one, electrical speed. Electrical speed and mechanical speed are different things. Okay. For example, if you use incremental encoder, your motor rotate 1 RPM. Okay. It will send you, for example, resolution 2048 pulse per revolution PPR. It will send 360 degree for 360 degree. It give will your microcontroller 2048 pulse is resolution 1 over 2048. It's seen very high, but in the military operation and the avionic aviation, avionic operation, high prices electric vehicle operation is very low actually. Generally, they want from you 1 over 10,000 resolution. Okay, and we talked about the some position sensor. We can return the simplified motor model. I said you theta is our rotational speed, and the theta dot, the derivative, with respect to time of the position, is our rotational speed. It's very simplified knowledge. If you have a position information from your encoder, etc., you can obtain very easily speed. What is the speed? Theta dot, the derivative with respect to time, of the position, it will be your speed. Okay, we have got this feedback path here. So key sub B in your screen, you can see back EMF factor. So every brushed motor, now don't forget it, we are in brush motor. Okay, brush motor is the mother of the all motor types, so we focus to lots of time brush motor, and then we will see brushless PMSM induction machine, etc. So I said every brush motor is also a generator. Don't forget it. I said to you last time, we call it not motor, it's machine. Why? Because a motor acts as a generator. For example, I said to you in regenerative braking operation, they work as a generator. So DC motor rotate as a supply voltage to the battery. It is generator, like a wind turbine. So we call them machine, not motor. Okay. So back EMF I said. So If you take a motor and spin the shaft, in briefly, when you are not connected to the terminals, you can see it generates a voltage. Okay, in your screen you can see. For example, take a DC motor, connect the drill machine. It is connected with the drill and measure the DC output step by step, slowly. You will see voltage increasing. Okay, in your screen you can see, left side of your screen you can see this operation. If you want to define your electrical or motor constant, for example, in our commercial products, firstly, we want to define motor parameters. Most important one, key E, back EMF constant. We connect a drill, slowly we try to turn it. Also we connect an oscilloscope or voltage meter, and then we observe it. Okay, this is tricky. Now, we can either have voltage in and rotation out, or rotation in and voltage out, but every motor, also generator I said you, back EMF constant say us, this is turning. It generates a voltage with subtract from the externally applied voltage over here. So what turns into motor current through the armature is not simply the applied voltage divided by this impedance. In your screen you can see define motor time constant upside of your slides. Good. Now, well, this is the modeled here simply as a linear factor times the speed. So at zero speed, I need to check, yes. So at zero speed, the back EMF is zero, firstly. So we will get the full applied voltage divided by the impedance of the armature when the back EMF, when the speed is zero, so the back EMF is zero. In your screen, you can see V over R. It will give us, the stall current. Also, you can see mH over Km, Newton meter over ampere. It will give us another stall current. Okay, now it's a data sheet. You want to take a motor from market. They give us a data sheet. In this data sheet, you can see nominal voltage. For example, what's the nominal voltage? Nominal voltage, your motor applied voltage. For example, in this motor, 24 volt. Winding resistance value, 0.8 ohm. Another factor, output power. Output power, 174 watt. Don't forget it. Some students sometimes forget it. What's the efficiency? Efficiency is output power over input power. Why it's important? You want to take a motor from market as an industrial. Generally, people suppose that in nameplate, you know, every motor has a nameplate. In nameplate, they have a power. This is your output power. Probably your motor efficiency, for example, for DC motor, 70%. Output power I suppose that 200 watt. Actually, if your motor efficiency 70%, your input power will be nearly 200 over nearly 300 watt your input power. You will supply from the grid or battery 300 watt. So if you want to calculate your battery capacity, please focus it. Not output power. Input power is important for us. Your efficiency, if for example 70% in nameplate is written 200 watt, actually your input power 300. Some students come to my office, hocam, I buy a battery, my motor actually 200 watt, why my battery decreasing very fast? Because students don't focus the input power. Nearly, he forgot the efficiency factor. Okay. Actually, in brushless DC motor and permanent magnet synchronous machine, efficiency is very high. However, in induction machine, also we call this a asynchronous machine, and DC motor efficiency are very low. This is important. So, if you want the high torque, high power, high efficiency, you need a PMSM or BLDC or another permanent magnet electrical machine. Okay. Well, so maybe we can say here speed and torque curve. Actually, in DC motor, curves are very simple because it's decreasing linearly. Voltage equation is linearly, speed equation is decreasing linearly, etc. However, servo motor are same with DC motor. It's good. Another, however, asynchronous machine and induction machine is very different. Their characteristic. In I suppose that 8 weeks later we will focus the induction machine. We will show you their curve and their control algorithm is very different from DC and PMSM. Okay. Now after class, please focus. Please download a motor company. For example, I say to you Maxon Motor. Okay. Maxon Motor. You can download Maxon Motor datasheet. It is very detailed. You will see lots of these parameters. You can search in internet what is the nominal voltage, what is the no load speed, what is the stall torque, friction torque, etc. This parameter is very critical. Now, uh, static acceleration. Yes, maybe we can go with the. Okay, before acceleration, I checked another website. Now, I will share another section. We will go next week in starting acceleration. Now, I want to show you another web page. Wait me. MATLAB section. Michigan. Michigan. MATLAB. Yes, control tutorials. Okay. I hope I will share it. Slide, share screen, share application screen, Chrome control. Yes. Good. Please write. Okay. Now, I hope this page is my favorite website for MATLAB starting. I hope lots of students know a MATLAB. Actually, MATLAB is a very detailed software and analyzer and simulator. However, we can start it, we can start with a simple example. Now, you can see in your screen, I hope. If you don't see any screen in your OLearn, please write me. Control Michigan University as a website nearly 10 years. I think it's a very good starting point. Website name ctms.engin.universityofmichigan.edu. This is control tutorials for MATLAB Simulink. They have step-by-step development of MATLAB and Simulink. Also, they show detailed DC motor controller. Now, welcome. Please close it, wait me. For example, we can start with the introduction. I click it. You can open in your computer. Okay. System modeling. In this website, we have 1, 2, 3, 4, 5. No 5. Cruise control, motor speed control, position control, suspension control, inverted pendulum, aircraft pitch, ball and beam control. Nearly 2, 4, 7 example with all details. We will complete all this example actually, but in this course I will give you first homework as a cruise control, motor speed. Don't cruise control. Forget the cruise control. Next week your homework, motor speed and motor position control with all details. In first homework is very easy because in this website every detail, every step are available. However, I am waiting from you. You will use another motor. For example, any Maxon motor. Okay, firstly, you will download MATLAB Simulink. In your computer, why my screen is white? You can see which screen? Please say in comment. No. Ahmet ekranında Introduction System Modeling yazmıyor mu? Tamam. Bir dakika kapatınca gidiyor mu? Tamam şimdi anladım. Peki. Okay. Now, in your computer, do you have MATLAB Simulink? All students, please say comment screen. Everybody have it? Which students in class? I check. Yes. Rahma. İsmail. Ahmet bilgisayarında do you have MATLAB Simulink? Nasıl indireceğini biliyor musun? Do you know where will you download it? Kalırsın dersten haberin olsun MATLAB Simulink yoksa. If you have no MATLAB Simulink in your computer, probably your grade will be FF. It is obviously FF. Bulutan, do you have MATLAB in your computer? Yes or no in comment screen. I am waiting. Tamam. İsmail var dedi. Muhammed Kusay Mevlüt. Do you have MATLAB Simulink? Muhtemelen. Muhammed Gusay, yes. Rahma, yes. Samer, do you have MATLAB Simulink in your computer? Tarık and Samer, please say yes or no. Okay, yes. Samer not available. Don't important. Okay, yes. Now, please open this page and then motor speed. A system, if you want to system model, system simulation, you can start with the system. What's the system? First 2 week, first from first week we have a. This is the third hour actually. Generally, all DC motor parameters are set. We can start in our homework. Don't forget it. This homework is very easy. First step, you will find a DC motor from internet. I propose you Maxon DC motor. Okay, Maxon web page. You can download a datasheet for any DC motor. Their datasheet are very interesting. All parameters are available. Okay, and then please open MATLAB. Second thing. Third thing, please open this web page. Step by step, you can click motor speed, you can click left side system. So system firstly modeling. And now, firstly, which key MATLAB command use in this tutorial? Don't forget it. This is very easy. Please follow the instruction of in this page. After this week, I will give you your own MATLAB simulation. It will be very complicated. Now, this is DC motor. Okay, I said I try to tell something about it lots of time. Physical setup. In DC motor, we have V, voltage source, also R, L, armature current, back EMF, inertia, viscous friction, torque, and field current. In this motor, please don't use this parameter in your example. This is this web page parameter. I am waiting from you another motor parameter. Also, I will upload homework format in OLearn. Please use that format. I am waiting from you a report. Also, moment of inertia is necessary. With motor viscous friction necessary. Back EMF constant necessary. Torque constant necessary. Resistance inductance. Okay. System equation. If you have a time, if you like the DC machine, please collect step by step what is the equation. In here, T is torque. Torque equal Kt times I. I said you torque and current are in relation. What is the relation parameter? Kt, torque constant. If you multiply I current Kt, you will obtain T in DC motor. Also, I said you speed and back EMF are in relation. Derivative of theta and gives us speed and back EMF are in relation. If you speed times Ka is the back EMF constant, you will obtain back EMF. So it's voltage actually. Generally, in our homework, we will use SI units. You know the SI units. Okay. Now, first step, transfer function, state step function. Step by step, it's very easy. Don't worry about it. Actually, it's you know all things control system course. Design requirement. Our main aim in our design, settling time less than 2 seconds. What's the settling time? I said you transient. Maximum transient time in our homework will be 2 seconds. It's important. Overshoot. What's overshoot? You will remember. For example, your reference speed 500, your maximum transient speed 600, your overshoot nearly 20%. I am waiting from you maximum overshoot 5. What's the 5? For example, reference speed 500. Your maximum steady state transient speed 500 times 5 over percentage 525. Okay. Also, what's the steady state error? Less than 100. What's the steady state error? For example, your reference speed 500 in steady state operation. For example, your motor rotate 10 minutes, 15 minutes, 20 minutes. Okay. Your speed error maximum 100%. What's the meaning? 105, 495. This is your interval of speed variation. This is your steady state error. Okay. In MATLAB, we start with the MATLAB. MATLAB and Simulink are different things. Okay. Yani we can use all together, but MATLAB is a coding section. Simulink is modeling section. Okay, don't forget. Firstly, we open MATLAB. We try to find transfer function. Yes, I know normally transfer function is very high mathematical requirement. However, in MATLAB, we have a function, TF. If you use TF function, you can obtain transfer function of your system. In DC motor, we have a parameter we write G is equal. Just that you know the MATLAB use C and C++. Like a C from microcontroller course, you know, G equal 1.11, 1.0.01, B, K, R, L, and then S. What is S? We are waiting from you formula. This formula comes from our simplified motor model. Okay, you remember from the first slide of today's course. We obtain MATLAB, we obtain transfer function of the system, and then state space. State space is very, I suppose that Math 3 or Math 4 course, state space equation. Here we have a SS function. First one, TF function. TF give us transfer function. SS give us steady state function. We obtain continuous time state space model. Okay, we completed our modeling section and then analysis. Actually, don't worry. Here they give us their MATLAB code where probably next page M file you can see here. Firstly, what is the DC motor speed system analysis? Second section, first section modeling, second section analysis. Our mathematical background of motor, open loop response. Okay, now, do you remember open loop and closed loop? If your system has a feedback like a position, like a current sensor, etc. Also, we have a reference and we have a feedback. This is called as a closed loop system. However, generally, in all analysis, we'll start with the open loop system. In this page, they propose open loop response. Okay, now we are use another function of MATLAB, linear system analyzer. It give they apply a step. Also, it give us step response of DC motor, our DC motor. For example, you can see here, please check my arrow. This is steady state. Okay, this is transient. Okay, what's our main aim? 2 seconds. 2 seconds is good. Also, my steady state error here, final value 0.0999. My reference 0.1. We have an error because our dashed line and my feedback blue one are different, but the my steady state as error acceptable level. Settling time 0.7 2.07, nearly okay. However, this is the open loop response. For open loop, it is good. After adding controller, it will be regulated. Okay, this is the open loop. In open loop system, we apply step. What's the another? Do you remember the another applying function? Step, ramp. Also, we have one more step, ramp. Last one. Do you remember? Step, step, ramp, uh, step, ramp. What's the last one? Do you remember? Step, ramp. Okay. No, not yeah, parabolic falan is not important for us. Step ramp and last one convolution. We can check step ramp. Allah Allah. Bir tane daha vardı ya. Ramp function. Step 1 over s. Ramp 1 over s square. Step ramp. Maybe we can check from image. This is step. You see. This is ramp. Impulse. Impulse. Last one. You can apply step for open loop test. Ramp is another option, and impulse. Yes. Generally, step is okay for us. In our commercial application, we use step input. Generally, electronic engineer use impulse. In electrical engineering, controller engineering, generally we don't use impulse. In some application, we are using ramp. Step 1 over s, ramp 1 over s square, parabolic is another one. Here, critical topic, constant position. Bakın, 1 over s, constant position. 1 over s square, constant velocity, ramp equal velocity. You want to design an electric vehicle. You will apply step, ramp, and parabola. Why parabola? Acceleration. You want to design an acceleration controller in your vehicle. For example, in your elevator, you will use acceleration controller, parabola. Okay, it's interesting. You will see here step input. If you apply step input your motor, your output in open loop like this one. Okay, it's good. We continue with the here important. We have a DC motor model. We applied step. We obtain controller. We obtain function, output function like this one. Step response output. Now we want to get pole zero map. How? We can use LTI model, linear system analyzer. In your MATLAB Simulink, upside of your program, you will see linear system analyzer. Please click the linear system analyzer. You will see identify of the location pole zero. You remember from your control course, all pole and zero will be available left side of your axis Cartesian coordinates. This system is stable. If any pole and zero are available on the right side of your Cartesian coordinate, it will be unstable. You need to design and controller. Okay, last step, LTI model. We go on. Response time, linear simulation. Okay, we completed the analysis. Then it's important, control. Now we want to design controller for our DC motor. We design DC motor. We use this parameter. Uh, Now another step. If you want to create a step response, you will use step grid for your figure operation, title, etc. are not important. We can check step by step, step by step. Yes. Now in PI, now we are in closed loop. We need PI and D parameter. We can assign KP, KI, KD. Also, we will check parameter of parameter effect of controller. You see in your screen, my settling time is very low now. For example, you see 0.5 now 2 seconds. Say before 2 seconds before controller. Now 0.5. My transient time reduced. This controller effect. Now we design controller in MATLAB. Next step, root locus curve. Root locus controller design, step by step. You see in your screen every step. For example, you will copy from here. If you are copy from here, your homework, but first thing, you will change your DC motor parameter. Okay, this is necessary. Also, and then, if you don't like the control, okay, don't worry. You can copy from here. Your simulation will work, don't worry. However, if you want to learn lots of things from electric drive system, please read step by step here. Why is the settling time? What's the overshoot? Do you have any question? Please ask me. Why is the root locus? Root locus is very important controller. You will remember from old course. This is my imaginary axis, real axis, root locus editor. I will locate my pole, my zero using PI regulator, effect of the PI. Okay, please step by step design your controller. Please read them, please copy them, please change some parameter, please play with the compensator parameter, pole zero location, etc. Next one, frequency. What's the frequency? Body diagram. Okay, with frequency body, you can develop body diagram. Another controller design section, root locus and body. If you develop the body diagram, you will see frequency effect. You can develop your body. To the next week, please come to digital. Okay. Simulink next week we will start. It will be second homework. This week, DC motor speed control from system to Simulink. It not contain Simulink. Okay, Simulink next week. Next week to the Saturday, I am waiting from you. Motor speed, modeling, analysis, PID, root locus, frequency, steady state, and digital. Okay, next week our course program, we will continue with the DC motor and then Simulink section. Okay, do you have any question? We need to complete it. We have only 1 hour time. If you have no question, have a nice day, dear all. Thank you for your attendance. Good luck in your homework. Okay, see you, dear all.